Lesson 7.1, Part 2, Vectors in the Plane, Magnitude and Direction. So let's start with magnitude. First thing to understand is that when I use the word magnitude with respect to a vector, what I'm actually talking about is the length of the vector. So distance from the origin to the end of the vector, whatever the length of that vector is, that is the magnitude of the vector. If I want to have a larger vector, just make the vector longer. If I want to have a smaller vector, make the vector shorter. So a vector, again, the magnitude of a vector is the length of the vector or the distance of the terminal point, which the terminal point would be this point right here. Distance of the terminal point from the origin. So length and distance, again, are the same thing. Now, another thing we need to think about when I say distance from the origin, that's actually a fancy way of saying absolute value. When I ask you the absolute value of -4, the old way of thinking about that is just to say, oh, drop the negative and make it positive. But what's really happening there, when I say what's the absolute value of -4, 1, 2, 3, 4, what I'm actually asking is distance to the origin. How far is this number from 0? So whether I ask you absolute value of -4 or absolute value of +4, the absolute value is the distance from 0. Absolute value is a distance from 0. Magnitude is a distance from 0, the distance from origin. When I refer to magnitude of a vector, I'm also referring to the absolute value of the vector. Keep that in mind in just a few moments. Just to throw another vocabulary word at you that may or may not come up in the future, the word modulus is the same thing. If I ask you what the modulus of a vector is, that's the same thing as the absolute value of the vector. That's the same thing as the length of the vector. That's the same thing as the magnitude of the vector. So regardless of which one of these I ask, I'm asking the same thing. Magnitude, length, distance, absolute value, modulus. Now, keeping that in mind, notation. Whereas this represents just the name of the vector, we're going to borrow that absolute value connotation to signify magnitude of a vector. If you ever see the absolute value sign around a vector, I'm asking for the magnitude of the vector. So, if magnitude of the vector is the absolute value, well, to figure out the absolute value, I need to figure out the length of this vector. Now consider that this vector is the hypotenuse of a right triangle whose components are, or horizontal and vertical components are A and B. I can figure out the length of that vector by using the Pythagorean theorem. And because we're using absolute value as our notation, I know that the length of that vector v, or the absolute value of vector v, can be found using the Pythagorean theorem or the square root of a squared plus b squared. Notice we're writing this as square root of a squared plus b squared instead of writing magnitude squared equals a squared plus b squared. It's more direct. Direction angle will just be this angle right here, the angle in standard position. Now, keep in mind, if I'm asking you for the direction angle of a vector, you can assume that I've given you the a and the b value. Now, to figure out that angle, I can use any of the three main trig functions, sine, cosine, or tangent. Sine and cosine, though, require that I know the hypotenuse. Now, of course, I could figure out the hypotenuse by determining the magnitude of the vector, but if you're given a and b, might as well just use those two sides. So if I use a tangent ratio, I can set up tangent of theta equals b over a, and thus theta itself would be the inverse tangent of b over a. Now, back in a prior unit, we learned about the restrictions related to inverse tangent. If I were to type an inverse tangent ratio into my calculator, I'm only ever going to get a first quadrant or a fourth quadrant angle. So that, keeping that in mind, this isn't necessarily the true direction angle. Think of the inverse tangent ratio as a reference angle, and then you have to pay attention to what quadrant we're supposed to be in based on what I gave you in the vector to determine what the actual true angle is. Let me show you what I mean by that. Consider the vector 2, 3. Vector 2, 3, positive, comma, positive. It's going to be a first quadrant angle. So throughout this entire process, I need to remember that this vector should be in the first quadrant. Here I've provided a sketch of where that first quadrant angle vector would be. To determine what theta is, I'm going to use the inverse tangent ratio, inverse tangent of 3 over 2, b over a. And when I type it into the calculator, if I'm in degree mode, I'm going to get 56.309. Now, throughout this lesson, always pay attention to the directions. The directions will tell you that I want the answer in terms of radians or degrees. So pay attention if you're getting the wrong answer, even though you're pretty sure you're doing it right. Double check the directions. Does it say radians and it's supposed to be in degrees? Does it say degrees and it's supposed to be in radians? Pay attention to the unit. For the purposes of this instruction here, I'm just going to do everything in degrees, just so it's more straightforward. So inverse tangent of 3 over 2, when I type it in my calculator, I get 56.309 degrees, which itself is a first quadrant angle because it's less than 90, which matches my expected situation of a first quadrant angle based on the positive of the component form, so everything fits nice and neat. When I'm in the first quadrant, there's really no adjustments that need to be made. Fanciness comes up when I move out of the first quadrant. Consider this one. -2, 3, that's going to be a second quadrant vector, so a second quadrant angle. Keep in mind the angle starts at 0 degrees and goes all the way around to wherever it ends in the second quadrant. If I were to attempt the same formula, inverse tangent of b over a, or inverse tangent of 3 over -2, type that in the calculator, it's going to tell me that the answer is -56.309. Now, of course, that is not a second quadrant angle. -56 degrees is somewhere over here. All right, so I'm not going to present -56 degrees as my answer. I'm going to adjust based on the quadrant. Now consider, what I've actually found here is the reference angle. When I do inverse tangent, I'm getting the reference angle. Now, ignore the positive, negative, just focus on the magnitude of that value, 56.309. So this angle right here is 56.309 degrees. Now, of course, all of this is 180 degrees. So if I want to figure out what theta is, it's just a matter of taking 180 and subtracting the reference angle, like this, 180 minus 56.309. Now, look at that statement that I have right there, that 180 minus 56.309. Let me just reorder the terms, just because I want to. Instead of 180 minus 56.309, I'm going to do -56.309 plus 180. Well, this piece right here is exactly what this piece right here says. So with that in mind, if I know whatever answer I get right here, in order to get the true angle, I'm going to have to add 180. In practice, going forward, that's exactly what I'm going to do. I'm not going to waste my time trying to figure out what the reference angle is and then subtracting that from 180 and all. I'm just going to build it into the process from the beginning. I know I'm in the second quadrant. If I'm in the second quadrant, I'm going to add 180 to my inverse tangent to build in an appropriate ratio. I'm sorry, build in an appropriate adjustment, and I end up getting 123.690 degrees, which is greater than 90 and less than 180, so I know that's a second quadrant angle, which matches my second quadrant vector, so I know I did this properly. Looking ahead to the third quadrant, negative, negative, that's a quadrant 3 vector. Setting up my inverse tangent, -3 over -2. Now notice the double negative would actually cancel out and give me the same answer that I had from quadrant 1. I am not in quadrant 1, I am in quadrant 3. Now, just like we did before, that 56 is technically just the reference angle. In order to figure out the actual angle theta, I'd have to recognize, okay, from here to here is 180, and then I have to add the reference angle to get the full angle. It's 180 plus 56.309. So in this case, if I had just added 180 to the angle to begin with, that would have built in the adjustment all the way through. So I get 236.309. Again, greater than 180, less than 270, so I'm in quadrant 3, which is exactly what I expected it to be. When I'm in quadrant 4, start with my basic ratio, inverse tangent of -3 over 2, b over a. And just like before, I'm going to get the same negative 56.309 because it's going to be the same reference angle each time. I'm in the fourth quadrant, so that's why it's going to come out to be negative. This time, though, keep in mind, negative 56.309, that actually is a fourth quadrant angle. Negative 56 degrees is this guy right here, which is actually technically a correct answer. But I never like having negative angles as my answers, so what I'm going to do is I'm just going to add 360. Because, of course, adding or subtracting 360, you're not actually changing the value. You're finding a coterminal angle. Adding 360 would make that a positive angle. Now, to reason it the same way I did all the other ones, again, 56.309 is my reference angle. If I wanted to figure out the angle theta, I'd recognize, well, all the way around is, again, 360 degrees. If I subtract out my reference angle from 360, that will give me theta that remains. And just like I did before back in quadrant 2, this is what I have, but reorder the terms. Negative 56.309 is this guy right here. So if I just build that into the problem to begin with, then I don't have to worry about making the adjustment after the fact. And in this case, it spits out 303.690, which again is between 270 and 360, a true fourth quadrant angle. So to summarize, when I'm looking for a direction angle, I'm going to use inverse tangent of B over A. But based on the quadrant, I have to make an adjustment. This inverse tangent formula only represents my reference angle. The adjustment puts it in the appropriate quadrant. And then the adjustment, if I'm in quadrant 1, there is no adjustment. The reference angle is my angle. If I'm in quadrants 2 or 3, I'm just going to add 180. Because again, if I'm in quadrant 2, inverse tangent is going to produce a negative angle. Add 180 will give you an angle between 90 and 180. Quadrant 3 will produce a positive angle, so adding 180 will give you an angle that's greater than 180 but less than 270. Also note, if I'm in radians, I'm obviously not going to be adding 180, I'm going to be adding pi. Degrees, radians. Depending on what mode you're working in, what the directions tell you to do, make the appropriate adjustment. If you're in radians, don't add 180, add pi. If you're in degrees, don't add pi, add 180. And in the fourth quadrant, 360 will be the adjustment. If I'm in the fourth quadrant, it's 360. Just remember, if you're in quadrants 2 or 3, the x-axis is 180. If you're in quadrant 4, the x-axis is 360. All you're ever doing is adding the x-axis. In quadrants 2 and 3, the x-axis is 180. In quadrant 4, the x-axis is 360. That even works in the first quadrant. In the first quadrant, the x-axis is 0. The adjustment is 0. So, we now have a formula for magnitude and a formula for direction. Let's put it to work. Here's a question. Find the component form, the magnitude, and the direction of the vector with given and initial terminal points. So just like you did yesterday, here's an initial point and a terminal point. I'll give you 10 seconds. Pause the video here. Hit play when you're ready. Find the component form, just the component form. All right, so the component form, we'll use the head minus tail method. So head is the terminal point, tail is the initial point. Head minus tail, -3 minus 2 for the A component, and 4 minus 5 for the B component, gives me -5, -1. So my component form is -5, -1. Once I have my component form, I can now find both the magnitude and direction. You have to know the component form to find the magnitude and the direction. For the magnitude, I'm going to use the Pythagorean theorem square root formula. So it'll be the square root of -5 squared plus -1 squared. Quick reminder, if you type -5 squared into your calculator, you will not get the right answer. The right answer, -5 squared, is supposed to be 25. If you type this into your calculator, -5 squared, you are not going to get 25. If you type -5 squared, you're going to get -25. Please make sure that you are using parentheses. -5 parentheses squared is 25. If you're not using parentheses, you are describing something completely different. We've talked about this before. Please make sure that you are doing this properly. So -5 squared plus -1 squared, that's going to give me 26. So my magnitude is the square root of 26. You can stop right there. There is no need to go any further. Square root of 26. If you want to go further, that would approximate to 5.099. Now the direction angle. Again, we'll just use our inverse tangent formula of b over a, -1 over -5. Now, before I type that in my calculator, though, I'm going to take note, -5, -1 is in quadrant 3. If I'm in quadrant 3, my adjustment is 180. Remember, quadrant 3 is still attached to the x-axis on the left side of the coordinate plane. So the x-axis from quadrant 3 is 180, so it's going to be 180 as my adjustment. Type that in the calculator, you should get 191.309. Please take a moment, pull out your calculator, type this in, make sure you're getting the right answer. You don't want to be the person on the test that doesn't know how to use their calculator because you never actually practiced using your calculator. Pause the video here if you don't already have your calculator on your desk. Type this in, make sure that you're getting the right answer. If you're not getting the right answer, double check that you have the right mode. This is, I did this problem in degrees. If I do it in radians, it will look like this. Inverse tangent of -1 over -5 stays the same, but because I'm in radians, I'll add pi and I'll get 3.338. Go ahead and replicate both versions of this answer so that you know that you are doing it properly. All right, moving on. Here's another problem that looks exactly the same. Pause here, hit play when you're ready. All right, so starting with the component form, we'll do head minus tail, and we get -4, 3. To find the magnitude, we'll use the Pythagorean theorem. Now, in this case, I really shouldn't need to do the Pythagorean theorem because this is a triple. 3, 4, 5. The magnitude is going to be 5. I can verify it by using the Pythagorean theorem, but I get 5. Then the direction angle, inverse tangent of b over a, 3 over -4. Since the component form tells me that I'm in quadrant 2, I'm going to make an adjustment of 180, which gives me an angle of 143.130 degrees. Or, if you do it in radians, adding pi as my adjustment, 2.498. When it comes to math, you should always be able to work forwards and backwards. So whereas with the previous problem, I gave you the component form and asked for both the magnitude and direction. This time, I'm going to give you the magnitude and direction, and I want the component form, forwards and backwards. So remember the notation here, absolute value. So this is the magnitude, and this is the direction. Now, the way to think about this is I have a vector. Now this vector, I know it's in the first quadrant because it says 87 degrees. Now this one is clearly not drawn to scale because it should be a lot closer to the y-axis, but I wanted to draw it like this to help illustrate what's happening here. Here's my vector. It has an angle of 87 and a magnitude of 5. So the length of that vector is 5 and the angle is 87. Anytime I have a vector, I have an invisible triangle. And the question said, give the component form of vector v. The components is made up of the a value and the b value. To figure out the a value, let's start with the a value, ignoring b for a second. To figure out a, recognize I have the hypotenuse and an angle of a triangle, and I'm looking for the adjacent side. Let's just use a cosine ratio. Cosine of 87 equals a over 5. Solving for a, we get 5 times the cosine of 87. Now, likewise, we could have done exactly the same thing to find b, except instead of using a cosine ratio, I would have used a sine ratio. Everything would have worked out the same. The only difference, again, cosine gets replaced with sine. So if the a value is 5 times the cosine of 87, the b value is 5 times the sine of 87, which allows us to generalize this process. Given a magnitude and a direction, you can find the components by using these two formulas. The a component is the magnitude times the cosine of the angle. The b component is the magnitude times the sine of the angle. So let's put that back to work for these two problems. So magnitude 5, angle 87. So then the component form initially would be 5 cosine of 87 times comma 5 sine of 87. Typing each of those into a calculator, notice these are degrees. Make sure your calculator's in degree mode. You should get 0.262 and 4.993. Notice the reasonableness of this answer. First off, it's a double positive, which means I'm in the first quadrant, which matches the angle that was given. Also, if I have an 87-degree angle, I would expect the A component to be super small and the B component to be large, but very not large as in hundreds and hundreds, just large in the sense that it's going to be really close to whatever the actual length of that hypotenuse is. Well, 4.993 is pretty close to the maximum length of 5 being the length of the hypotenuse. So that is a super reasonable answer. I'll give you a moment, pause here, play when you're ready, try the next one. All right, so quick and easy, just plug it into the formula. Magnitude cosine of the angle for the A component, magnitude sine of the angle for the B component, and you can just type that in the calculator and I get negative 2.121, comma 1.244. Notice, again, 150 is in the second quadrant, and this vector is in the second quadrant. Now, just to point out, hopefully you noticed it, 150, that's a unit circle value. You didn't need a calculator on this one. You could have done this one without a calculator. 150, the cosine would be negative root 3 over 2. The sine would be 1/2. Cleaning that up, root 6 times root 3, that's going to be root 18. So I can have this as my answer just as easily as that decimal version. Keep in mind your test is going to be with and without a calculator. So if this was on the calculator portion of the test, I would present this as my answer. If this is on the non-calculator portion of the test, I would present this as my answer. All right, so let's summarize what we have so far. Given a vector AB, we have the pictorial representation of that vector right here, where the terminal point of the vector is right here at the coordinate AB. That vector can be represented also using a triangle whose horizontal and vertical components are A and B themselves. The magnitude of that vector uses the absolute value as my notation, and you can use the Pythagorean theorem using A and B as the two sides of the triangle to find the length of the hypotenuse V, so square root of A squared plus B squared. The direction angle will use the inverse tangent ratio of B over A, and then we will add an adjustment based on what quadrant we're in. If we're in quadrants 2 or 3, we're going to add 180 because the x-axis would be 180 based on either of those two quadrants. If we're in quadrant 4, we'll add 360 because from quadrant 4, the x-axis would look like 360. Again, that's in degrees. If it's radians, it would either be pi or 2 pi respectively. If you have the direction angle and magnitude, you can find the component form, or what we'll in the future start calling the rectangular form. Don't worry about that just now. If you have the magnitude and direction, you can figure out the component form just by multiplying the magnitude times the cosine of the angle for A, the magnitude times the sine of the angle for B. So let's look at a problem that's going to require the use of all 4 of those formulas. Given vector V, which is 5, 4, and vector W, which is 2, -5, I want to find a new vector, let's call it U, that is in the same direction as W and with a magnitude of V. So I want the direction of W and I want the magnitude of V. So let's do those 2 questions first. Starting with the magnitude of V. So V is the vector 5, 4. The magnitude would be the square root of 5 squared plus 4 squared, or the square root of 41. Don't be tempted to convert that to decimal. The earlier you convert a value to decimal, the less accurate your final answer is going to be. So let's just leave that as square root of 41. Next, we'll find the direction of W. Notice the way I've notated this. It's the direction angle theta with a subscript of W, indicating that this is the direction of W. W was the vector 2, -5, so I'll set up my inverse tangent of -5 over 2. Then I need to make an adjustment based on the quadrant. 2, -5 is in the 4th quadrant, so I'll add 360. Again, I'm just defaulting to degrees. I could just as easily do this problem in radians, and I would end up with the same answer. So if you're in degrees, we're adding 360. If you're in radians, we're adding 2 pi. Now when I type that in my calculator, I'm going to get approximately, really that should be approximately, 291.801. Double check, is that reasonable? Well, I'm in the 4th quadrant, 2, -5, and 291 is also in the 4th quadrant, so that makes sense. Now, remember what I said about that square root of 41. Do not convert to decimal too early in the problem, because the earlier I convert to decimal, the less accurate my final answer is going to be. Well, this is converted to decimal. So, which means do not, under any circumstances, use this value right here. We talked about earlier in the year how to reuse a value that came up earlier in a previous problem. And it's been a while since we've done that, so let me remind you what we need to do. Let me pull out my calculator. Poof, magic. All right, so here's my calculator. Now remember, I would have typed this directly into my calculator. Now before I do anything, let me double check. I am in degree mode. So I'll do inverse tangent of -5/2. Close that parenthesis, add 360. And that's where I got the 291.801. But again, it doesn't stop at 1, it keeps going. Those values are still important. We're not rounding off halfway through a problem, we round off at the end of the problem. Do not, under any circumstances, round off this intermediate answer. So in order to use this answer in a future step, I'm going to go down here to the store button. I'm just going to hit store. It's automatically going to take whatever my previous answer was and store it. I can store it for any letter I want. Now this is W. I could hunt for the W, which is right there. So there's the W, but I don't like doing that. I'm just going to store it for A, alpha A. I hit alpha A and then hit enter to lock it in. Notice if I clear and then re-hit alpha A, enter, it's still there. So I've got alpha A used on my calculator, so I'll make a little note to myself on my paper that I just stored this for A. So now let's move this off to the side and keep going. So now my final question was not to find the magnitude of V or the direction of W, it was to find the vector U. So we now have a new vector, let's call this new vector U, and it's got to have this magnitude and this direction. So just like we did on the previous set of problems, magnitude cosine of the angle, magnitude sine of the angle to figure out the values. And then I can type these in one at a time using my calculator. Square root of 41 times the cosine of alpha A is going to give me 2.378. And then square root of 41 times the sine of alpha A is going to give me -5.945. So there I have my final answer. Notice I didn't retype this angle when I was calculating this. I used the calculator to store the value so that I would get the most accurate answer possible. So here's one more that looks almost exactly the same. I just changed the numbers. Try this one on your own. Pause here, hit play when you're ready. All right, so magnitude of V is going to be the square root of 20. Direction of W, we're in the second quadrant, so adding 180 is going to get me to 161.565. Again, store that for A. Even though I've already got a value stored in my calculator, it doesn't really matter, because if I do inverse tangent of 1 over -3 plus 180, I can actually go ahead and hit store alpha A right here instead of doing it as separate steps. Hit enter, hit clear, alpha A has now been overridden with my new value of A. Keep going. U is going to be that magnitude with that direction, so square root of 20 cosine of A, square root of 20 sine of A, and then I get my final answer after I type each of those in my calculator of -4.2426. I guess I threw in an extra variable digit for some reason, and 1.4142 would be the next digit. Remember, as long as you have 3 past the decimal, I'm perfectly happy. If you put the fourth one, great, but I need 3 past the decimal.